Everyone. I now welcome Francois Ledrappier to give the second talk of this session. And his talk is titled Exact Dimension of Oseledets Meshes.
Thank you. And thank you for the invitation. I'm very happy to be here. And I have known Dani for forever, and his mathematics for even longer than that. 10 years ago, we discussed when we met, but I forgot what we said, but okay. But it's so in the distant past. So I want to talk about random walk on a group of matrices. And in fact, I don't care much about the determinant, so I can take group of d by d matrices of determinant 1, and I have mu probability measure. On and before I forget, I will make, for all the talk, some hypothesis on mu. One, which is necessary if I want to talk about Oseledets theorem, and for what I will talk, I want to have the log some moment condition. And I have two other hypotheses which are technical, technical in the state of the proof, but I don't think they are essential for what I have to say. But for the moment, I need to say that the first one is that mu has countable support. This one is really annoying, and I really don't know how to get rid of this hypothesis. And the other one is that the h of mu is finite, where h is the usual entropy. Now it's a sum because it has countable support, so it's minus log mu g mu. And this hypothesis is for convenience because at some point there is a computation which we can do with finite entropy, but we certainly with some work we can get rid of it. But we means it's a joint work with Pablo Lessa. From Montevideo. So what do we have? I was saying that I will talk about a random walk. So what is a random walk? So I consider the space, I have a probability space. Which is the space of sequences of matrices. And I put on it some measure. And the measure is the product. So this is a space of independent trials of matrices, each chosen with probability mu. Okay, that's 295 some omega equal gn of omega, the nth coordinate. And what is the random walk? So the random walk, so I write it because people depend on convention. So I look at this random variable with value in matrices. So I start with G0, G1, Gn minus 1. That's for n positive, Gn minus 1. Huh? And for n negative, I start with G minus 1. Gn. Yeah. For n negative. And if you want to ask, just put x0 of omega identity in such a way that I have the cocycle relation xn plus m of omega is xn of omega xm of sigma n omega.
Notation, the small xn.
It's a big xn. All this, yeah, it will be. It will be big. All x are big so far. Gn is the nth coordinate in the product space. This is the product space, and I write the coordinate as Gn. If omega n is, it will be confusing at some point. Okay, so in that setting, what we know, in fact, it's much more general than that because it's for a stationary cocycle. There is the famous Oseledets theorem. Which tells you somehow that you can diagonalize the product, the xn in some sense, in some asymptotic sense, look more and more like a diagonal matrix. So so Oseledets theorem gives you data. So your data you get is there are numbers. Real numbers, T1, capital N, and integers D1, N, with some stupid relation, D1 with Dn is the whole dimension, and the sum of Di, Ti, 0. So that's the growth rate, and that's the framework. And the main object, which is given by Oseledets theorem, is a random and random decomposition define M almost everywhere of Rd as E1 of omega plus E2 of omega plus E capital N of omega. Okay, I have the decomposition and the relation between all these objects. Such that, okay, the dimension of EI of omega is Di. And the EIs are characterized if and only if are characterized by the property that limits n go to plus and minus infinity of 1 over n log of. So I take my matrix Xn, which is written over there, I take my product, I apply it to the vector V. And EI is characterized by the fact that the vectors in EI are the ones which exactly have the asymptotic growth or decay at, at minus infinity, which is given by Ki. So if you add one matrix, it's in some sense a decomposition into eigenspace with the same modulus of eigenvalue. But it's not one matrix, it's random. And the theorem is true, in fact, for any stationary family, but we use it only for the independent case. So if you are not familiar with it, think D equal 2, and you have 2 by 2 matrices, and eventually there are more and more diagonal. In some sense, there is a direction which grows like e to the n lambda. There is only 2 numbers, key and minus key, because the sum is 0. The integer are 1, and you have 2 directions, which are random. And in one direction, it grows like e to the n lambda, and it decays like e to the minus n lambda, and the other direction is the contrary. That's what the theorem says, and it's true in all images. So what do we get? We get that object. So that object, EI, so EI is what? So it's a decomposition. It's so it belongs to the product of the Grassmannian of dimension DI. Just more than that, because there are, it's a direct decomposition, but it belongs to that. So that space is a very nice space. It's a product of Grassmannian. So it has algebraic. It has natural metric, for instance, the metric invariant by rotation. So you can you can try to understand what the distribution. So the object of interest for us is capital M, which is the distribution of that object. So I have a random object in some nice space. I look at the measure on the space, which is the image by the map. And the theorem I want to talk about is that this measure is exact dimensional. What does that mean, exact dimensional? The theorem is Pablo. Some version of it is about to be published, but the one I'm talking now is a little more general. M is exact dimensional. What does that mean? It means that M almost every point in that big space I was happy to have a long blackboard, but so for M almost every point in X, what we have, we can the limit as epsilon go to 0 of the log of the measure of the ball of radius epsilon divided by log epsilon is some number that there is delta. What's that? For M, you have this limit. So it's an almost everywhere convergence. I mean, if you have convergence, it's clear that it's something which depends on omega. As the function on omega is stationary, so it's clear that it's a constant. But the result is that you have convergence. So what does that mean? It means that you look at a small ball, it gives you something about the measure of that small ball. So it's very weak. It's just the measure is roughly epsilon to the delta, but roughly in the sense of the limit of the log. So there might be some correction. I don't know. I mean, there will be some correction, which which we haven't studied and which are very interesting. But and also it's almost everywhere. We don't say anything about the behavior of the measure everywhere. Which is also interesting. I mean, there are results by Givard and new results about estimates like this everywhere. But what I'm saying is that almost everywhere we have some convergence, and the convergence to a constant. In that generality, I did not exclude the fact that all exponents are the same, so my space is just a point. But otherwise, yeah, I know that.
Once it's not
yeah,
space,
it's not zero. It's not zero. Yeah, because I mean, the entropy of the this is the first entanglement. Okay, I'll talk. You'll see why it's not zero. But a particular case is the case where the all exponents coincide, and then I'm talking about a point. A point has dimension 0, but it's true. I mean, it's not. So what I want to do is to say a few words about the proof. And okay, there is the main part of the theorem is also, and there are okay. There are geometrically defined numbers, gamma ij, I different from G, I, G, between 1 and n. So I have, it doesn't, this part doesn't say much, and this is the sum from ij of gamma ij. So the most interesting information is that this number not can be computed, but can be seen and has some geometrical meaning that we can hope to understand. But it's quite complicated to explain what these numbers are, and that's what I want to do. I want to do the proof by explaining what the gamma ij are on one example. So the first observation is that this space is nice, but I have a much nicer space. So X is in one-to-one correspondence to the product of flags, partial flags. And okay, I put a star here to if I look at all the decomposition which are disjoint, such that the EI are pairwise disjoint, it is one-to-one correspondence with a pair of flags in general position. So what is this correspondence? If I have to have my EI pairwise disjoint. And disjoint for subspaces means up to the origin, of course. And RD is sum of EI. I can associate two partial flags. So EI associates F, the partial flag which will be U1, U2, UN, D, and F prime with dimension of UI is the sum of the J, and the dimension of U prime I is the sum of G bigger than I of the n minus G up to mistake. No, G bigger than n minus I of dj. And just by, if I write this that way, you already guess what are the UI. The UI is the sum of G smaller than I of pi, and the UI prime is the sum of G bigger than n minus I of ej. Bigger or bigger bigger. Okay, so I look at, so I have a decomposition of my space. I look at the partial flag by looking at my decomposition from the left to the right, bigger and bigger subspace, or from the right to the left. EI corresponds to the key I, and the key I are ordered by are decreasing. The key are distinct and decreasing, and the E1 corresponds to the I. And that's the key point. Thank you, because I have. So what is this mapping? It's a one-to-one correspondence between. I mean, it gets complicated if this mapping is well defined, but if you want to invert it, it gets complicated if the I are not disjoint. But if the I are disjoint, it's a one-to-one correspondence between X star, set of EI, subject EI, zero, and the set of pair of flags like this in general position. General position means set of F prime given by this decomposition, and I want that UI intersected U prime n minus I except that I'm unable to do it at the blackboard, but that's what it is. So general position, those space on the right are not completely disjoint from the space on the left. And if you have a pair like this, you can recover EI as UR intersected U prime and I. Yeah. No, because I just, I mean, dimension, I can say what it means. Yeah. I want to be sure. It's the same. I look at the, a priori, I look at the spaces. I mean, that's a space on which I have a metric, a natural metric, right? The product of Grassmannian. So I have an open set in my product of Grassmannian, which is satisfying this condition, an open dense set. And that I know that I live in that open dense set, or I just care about that open dense set. And it is in one-to-one correspondence with an open dense set is the product of prime, and the mapping in that direction is clear. The mapping in the other direction is less clear. But on the open dense set, it's one-to-one, and it's clear. Okay, that's just a game. The nice thing about writing my space as a product space like this is that in the trivial observation that now if I take f of omega depends only on Gn for n negative, and f prime. Non-negative. Why? Let's look at f prime. What is EI? A vector is in EI if when n go to plus infinity, when I'm saying that UI, maybe, U prime n minus I is a set of vectors V such that the lim sup and n go to infinity of 1 over n log xn of omega V is at most EI. Because U prime n minus I is the sum of all the spaces EI, EJ for J bigger than I. So J bigger than I means that the sum of all the space when going to plus infinity. The limit is Ti, maybe less, but at most Ti. And if I have a vector which, so the lim sup going to plus infinity is smaller than Ti. If a vector has a component which is not in that space, it has a component is one of the other. And so the growth is more than Ti. And when I make the sum, when I make the composition, the growth of the total vector is more than Ti. So that space, which depends on omega, is given by this equation, and xn of omega, xn is erased, but xn depends, n goes to plus infinity. N goes to plus infinity in the is n non-negative. So in the definition, I just look at G naught, G1, G2, Gn. So this guy depends on the, and for the same reason, if I go to minus infinity, negative infinity, I look only at the negative coordinate. But I am on the product space. So these two, f and f prime, are independent. Gn n negative and Gn n non-negative are independent. It's a product measure. So M is the product measure. M seen on that space is the restriction to that big open set of a product measure. So, and there is a measure of, so the theorem that we prove, in fact, is not this one. So let nu be the distribution of f of omega in f lambda in the space of partial flags like that with dimension going like sum of dj, then nu is exact dimensional. I mean, same statement, limit nu almost everywhere. Limit n goes to infinity, 1 over n log d of f divided by log epsilon. That's then there is a delta. Positive, such that for nu almost over f, this limit is delta. And the same remark, delta sum of gamma t for e smaller than t, where gamma t has some geometric meaning. Okay, and that's the result that I prove. It's the same for f prime by reversing the time and looking at the random walk with a symmetric measure. It is exactly the same. So new has some dimension delta, the distribution of f prime has some dimension delta prime. I make the independent product of the two, the measure of the ball. I take the log, so it does not depend the way I define the way the metric of the product is defined. The measure of the ball is roughly the product of the measure of the balls. So the log is the sum. So the capital delta is the sum of these two numbers, delta and delta prime. Okay, so already in dimension 2, you have something to prove. In dimension 2. What does it say? In dimension 2, we said we have one direction, E1, and another direction, E2. So now they are independent because of that. I mean, E1 depends only on the past, and E2 depends, the stable depends only on the future. So what I'm saying is that the unstable direction, E1, has some dimension. It was more, I mean, I stated it long ago, but it was more or less folklore because the limit I had was not almost everywhere. It was more or less, people knew that it was true, but it was proven by Hoolman and Solomyak because they needed it in some paper. So, I mean, it's not. It's not the main result of that paper, but that's where the proof is. So, and the proof is that the stationary measure, which is the Fürstenberg measure in that case, has some dimension. And the dimension is given by the Fürstenberg entropy divided by the exponent, two times the exponent. Okay, in higher dimension, it's okay. Well, why it's natural here? It's very natural here because the dynamics is what? The dynamics of the given by Oseledets theorem, forget about the omega, it tells some on the projective space, it contracts by e to the minus 2n lambda. The rate of contraction is e minus 2n lambda. So you have somehow to consider the measure of the small ball, and the measure of the small ball is given by the entropy. And okay, you have almost everywhere convergence for both. You can prove it, but still you have to be a little careful. But in higher dimension, it's more complicated because you have all kinds of all differences. Chi minus chi j are rate of contraction on the space of flags. It has been done, in fact, what has been done in a higher dimension, in not on the space of flags, on the projective the distribution of P1 in the projective. The distribution of P1 in the projective space is the distribution of the highest exponent. And this has been done, in fact, by Rappaport. Appeared last year, and I mean, he was more or less following, and there's the same kind of ideas in a paper by Feng, also still last year. In the case of IFS, which is very peculiar, you have action, but you don't have group, but you have action of mapping on which are contracting with different rates. So what's new in our statement is instead of looking only at one speed, now so our result, it's about flag. So now the difference here on the field you have different rates. But the different rates are well understood because they are what? K1 minus Kn, K1 minus Kn plus 1. No, yeah, K1 minus Kn plus 1, K1 minus Kn plus 2, and so on. They are understood. You have a natural hierarchy. And that's what is used in those two papers. And what we need to do is to build, in some sense, this hierarchy in the general case. And that's what I want to explain. No. The density of oh, if you know, I mean, if you know that the stationary measure is absolutely continuous.
No, if I assume that
no, okay. In the paper which appeared, we assume that the Q1 are all these, I mean, the N, capital N is D. So we assume that the EI are dimension 1. And then it simplifies a little. So the general case where dimension EI is not 1, there is one statement. I mean, most of the statements are the same, but there is one which is a little more complicated. And that's the one where we use finite entropy for the moment. But yeah, if I know that there is only one invariant measure and the flag is complete, it's simpler. Here I don't. Here I just say something. I don't assume anything about the group, but I only say something about the Oseledets measure. So in particular, if it's reducible. If you have two invariant spaces, you can switch the order. And the new invariant measure, it's not the Oseledets measure. So you have also, so, and I'm not, I mean, a priori, I could say, a posteriori, I could say something about that, but it's not in the statement of the theorem. Okay, so what's the picture which I make at this point? So already in dimension 3, there is a problem. I mean, I've been thinking of that problem for a long time. And what's the question? So, these three, so I assume that I have three. We have three exponents and the sum. So what is the space F? So the space of flags in R3. Flag in R3 is a line and a plane containing the line. So line is so I look at in the projective space R3. In RP2, what do I have? I have a line which is a point, and a plane which contains a line, which is a line now in the projective space. So I'm really considering the space of bar of points, line containing a point in the projective space. And now I have two. What do I know? What do I know about that space? I have some structure which is evident. will be the. I can project. I can project on lines or I can project on planes. So some structure which is clear on my, because I have this space which is three-dimensional, but it has three different contraction rate, K2 minus K3, K1 minus K2, and K1 minus K3. So I'm trying to put some order in that space, and what is clear, what is something very natural, is to project on the line or to project on the plane. These are nice, these are projections, give you foliation on your space. And they are codimension. Well, this is dimension 3, this is dimension 2, so it's codimension 1 projection. So dimension 1, it will be the same as the projective line. And what happens when you move by G, by Xn, or by G on by Xn, the picture is invariant. And here you have some action. And if you look at it, the action on the fiber, on almost every fiber, here recall I have my probability nu. So I have some factor here and some factor here, new line and new plane. And the action is contracting. And the speed of contraction, you have to look at it, but here it's K2 minus K3. And here it's K1 minus K2. So we are happy, right? Here we have the space for which Ariel Rappaport tells us that there is some dimension. Here we have one-dimensional fibers. And Pablo proved that along these fibers, the conditional measures are exact dimensions. So there is some number here, gamma. Gamma 2,3, but it's not gamma 2,3 star because it's not the final one. But there are numbers here which measure the dimension of the conditional measure. The conditional measures are exact dimensional. And we know that nu L is exact dimensional by Rappaport, and nu P also. And take the dual, and nu P also is the exact dimension. So we are almost happy, right? We have foliation, we can project on something. We know the dimension on the basis, we know the dimension of the fiber. Okay, we can go to bed. No, because typically when you have this situation, the dimension is bigger than the sum of the dimensions. It's at least, if you have some product space, it's true for dimension of set, it's also true for dimension of measure. If you have some product space, you have some set, you know the dimension of the projection and you know the dimension of the fibers, the dimension of the set is a priori bigger. Because the good, I mean, the definition of other dimension is clear. The good cover for the big set maybe are much more complicated than the one you get by taking a cover on the basis and a cover on each fiber. Let's give you a cover, but maybe not the best one. And it's typical. And if I have time, but I will not, I will show an example where one of the two, I mean, both dimensions are 0 here. It's a graph in both cases. But one of the two has the same dimension as the top, but not the other one. So it's one of the few examples where you can compute, I mean, and already the situation appears. So we have a problem. And what I can say is, I think the idea of our paper is already here. We consider a new vibration. Not much that we can do for fiber much. Right? You have a flag space, you have the line, the plane, what else? Yeah, we can do more if you can build a random fiber. Random by choosing F prime, the other part, the stable part. So this describes the unstable part. You can choose the independent stable part, and if I fix, so if I fix, so this is E1 and E1 plus E2. So if I fix it, as I said earlier, if I fix E3 and E3 plus E2, I can reconstruct everything. So if I know what is the picture, so I fix another blue is you don't see blue. I fix another guy until I have E2 here and E1. Oh, I know. So this is E3, this is E2 plus E3. And now what I'm saying is that there is another vibration, which is natural once theta. Which is I associate the line going through C and theta and the point of intersection. So my green object that's what I propose is for a new vibration, which is random. It depends on my choice of. So each time I have my flag space has all these different vibration, which but if I fix my F prime, I have a vibration. So the first thing it's codimension one. Codimension one because if I fix the green and the blue, I still have that point to fix. I can fix it by this angle, or I can fix it by this coordinate, but anyway, it's dimension one. So it's codimension one. And you can look at the contraction, the contraction rate is T1 minus T3. And the last thing is geometric. It's on that picture. So if I apply G, I get the same picture, but at G at the image. So I have a random foliation of my vibration, but which moves with G, but we are used to that. We like things that move with the action. So what happens is that what Pablo did for the random for the dimension of the vibration, here it's still exact dimensional. The conditional measure on the fibers have some dimension, which is my gamma 1, 3. And now I can continue the picture. Yeah? I have this two-dimensional object, also this one, three two-dimensional objects. Each one of them has two different contractions. So each one of them, I can define a vibration, but now, it's almost formal how to define it. Here I go to theta. Here I go to. These are one-dimensional fiber, and this is if I fix eta and eta bar, this is one dimension. Determining the line. If I fix eta, determining the line C eta is just one dimension, and if I fix eta bar, determining C bar is just one dimension. So these are one-dimension guy. Here. And now I have a family of vibration, of one-dimensional vibration, which are random, but are within one another and with nice relation. You can compute it's invariant. Everything is geometric. When I act by G, everything moves in the same way for compare with G eta bar. But everything is invariant, and you can compute the and the picture is made in such a way that it's easy to fill up. So I know I have a bunch of one-dimensional. I can describe my space by taking one-dimensional projection of one after the other. And on each one, I know it's equivariant and it's decaying with some well-defined rate. And for each one have okay, I can define some kind of entropy. I mean, entropy is always very friendly, and so there is some entropy, and for each one you have some dimension. Each conditional measure is all these conditional measures have some dimension. The problem is I'm allowed to add them, and what we know from dynamics is that we are allowed to add them if the contractions are weaker and weaker. I gave the positive number, so this positive number are decaying. So it depends. So I don't know where to go. It depends on the sign of chi2. So if chi2 is positive, then chi2 minus chi3 is bigger than chi1 minus chi3. Chi1 minus chi3 is the biggest of the three, always. But now between those two, it depends on the sign of chi2. If chi2 is non-negative, I can go this way. I always are less and less contracting. If chi2 is negative, I have to go this way to be always this way. And this way, since I start with chi1 minus chi3, it's the case of Ariel, it's good. So the dimension add up if I go down, if the contraction is weaker and weaker. So that's my gamma ij. I have first to draw that picture. Look at where what is the path going from the top to the bottom with decreasing contraction. For each one of them, I have some gammas. And the good gamma 2, 3, for instance, if K2 is positive, is this one. But if K2 is negative, it's this one. But it's if I know everything, I can fix it. So have so what happens in higher dimension? It's the same. So you have to find a combinatorial way of describing this, and there are many ways. And one which is present, it's not very clear, but one which is present is a partial orders on 2, 3, which are compatible with a suborder of the natural order. This picture is a graph of partial orders. Well, this is a trivial partial order. There is nothing. 1 is smaller than 1, 2 is smaller than 2, 3 is smaller than 3, but nothing more. And here, I mean, I can just follow. This is 2 smaller than 3. 1, 2. And I cannot have something here because 1 smaller than 2 and 2 smaller than 3, that's not a partial order. If I don't know that, and then, so at the end, I have the. Okay, and that's the picture in general. So in general, if you take any capital N, you can draw the Hasse diagram of all the partial order which are smaller than the natural order. But already for 4, there are 40 of them. And you have a diagram, and the number, the number is the list of number in the online encyclopedia, and it's already 3,000 and something for 5. And you have a picture like that. And the combinatorial fact, which is not very hard, but it has to be proved, is that there is always, so you have a picture like that, which goes from one order to the consecutive one. So the picture is the picture of the order classified. You have the notion of an order which is immediately smaller than another one if there is only one more relation. So that's what the arrow says. It's empty here. I had one relation, and one relation, and one relation. So you have this big graph. And for each time you had only one relation, you have some exponent, which is the difference of exponent, gamma A. And the combinatorial fact is that there always, you take two points in your graph which are above one another. There is always a path going from one to the other, such that the contraction are growing. The positive things are smaller and smaller. And once you have that, you can apply the result, and that's essentially the proof. And I have 2 minutes. In 2 minutes, I won't say any. Yeah. Yeah. Hmm? Because now I know from dynamics that if the contractions are decreasing, then it goes, then they can add up. And in that diagram, I can find a path with what we did with Lai-Sang. That's one of the steps in what we did with Lai-Sang long ago. And at the time, I thought it was a direct corollary, and you just. But no, I didn't think. I didn't discussing with Pablo that we could find this picture, and then yeah, it runs by itself. But, 1 minute. So since EO introduced another and Hinchin representation, I don't need to make to explain what it is. The nice example, if you take a gamma surface group, and if you take a Hinchin representation, gamma SL3, so EO describes the limit set. She defined the limit set in the space of flag, and it's a result of Goldman that the limit set is in the space of flag with my picture is a set of the border of a convex set and the tangent and the C1 convex set and the tangent line to it. And so so now in my picture I have So if you look at this picture, what you see is that if you know, so I fixed eta bar, if I know anything more, I know everything. If I know the direction, I know the point of contact, so I know the point. So what does that mean concretely? It means that I have some uncertainty here, but all the other entropies are zero. I can compute all the partial dimensions, they are zero. So there are only these two, and then I can say the delta is some entropy, the Furstenberg entropy, in fact, divided by inf of Q1 minus Q2. Because if Q2 is positive, I have to go this way and this. So this way, the only non-zero term is this one, correspond to K1 minus K2. And this one is zero, so that's also the dimension of Hoolman. But the dimension of the other one is the same H, entropy, because the entropy all comes from the basis. The same entropy, but now divided by K2 minus K3. So this one is smaller. So this graph has some, so both graphs are Hölder continuous, but this one Hölder continuous, but still doesn't increase the entropy. But this one, the dimension, but this one does. So it was really a problem, and I mean, one of the only example where you can compute everything, you see the problem. Over. Yeah.
More questions for the speaker?
You mentioned that the exact dimensionality is a. It seemed from what you said that you consider it as a crude statement. So what would be a refinement that you are?
The refinement will be control limiter. I mean, things like what the error. I mean, this is almost everywhere convergence theorem, which comes from ergodic theorems. Both, and you are in the independent world, so there might be maybe not central limit theorem, but at least iterated logarithm theorem. The mistake should be controlled by something, but epsilon log epsilon log log epsilon. I have no idea how to do that, but it's I mean, it should be. It's natural. It's natural to think that, but I have no clue.
Can I ask one more? So in the Benoit and Kahn have a very kind of accurate description of fine properties of the first, or I think it's called the first number measure on the flag variety. In the setting where the generated group is Zariski dense in essence, their analysis implies something like the exact dimensionality, or not related?
No, there is one. There is one technical point which is important. I mean, we don't use it, but Ariel uses it a lot. That's why you need finite support. Is that the first number measure, as a priori, the measure of the ball is at least epsilon to the small delta. There is some estimate on the measure of the ball. It's not completely, it's not Dirac. Not only it's not Dirac, but the measure of the ball is bigger than beyond. Yeah, it's smaller than epsilon to the delta, to some delta. Yeah, Benoit Kahn, they have some, I think there is a recent paper, a preprint by Klepstein and someone else, in the case, so that was, Guivarch was in a case of exponential moment. Benoit Quint has, I mean, at least the central limit theorem for L2, and I think also the large deviation, which gives you the, I'm not sure. And I think, no, I don't think they have the result I mentioned in general, but I think there is a preprint I've seen recently, I think by Klepstein, but maybe someone else, and he would kill me now, who does it with second moment in dimension 2.
Speaker once again.